Okay, 1 o'clock already, so we better make a start while waiting for more people to join. So good morning, good afternoon, good evening, depending on where you are. Thank you for coming to join the IMRR UNESCO Chair and SIM Webinar Series. So which will be delivered by globally leading academics in relevant fields. So today, it's really a great honor and my great pleasure to have Professor Limin Zhang from the Hong Kong University of Science and Technology to give us a talk. So first of all, I would give a very brief introduction about Professor Zhang before you all enjoy his webinar together with me. So Professor Zhang is a globally renowned academic leader in civil and environmental engineering. He is the chair professor and head of the Department of Civil Engineering and Environmental Engineering at the Hong Kong University of Science and Technology. He has been leading lots of cutting-edge research, on various natural hazards. So creating multi-hazard risk, reduction approach, to support, his hazard assessment, and then also, develop solution for this kind of hazards. So Professor Zhang currently directs the Digital Cities and Smart Hazard Mitigation Laboratory, where he and his team develop innovative solutions to tackle this kind of challenge created by the natural hazard I mentioned, and also enhance urban resilience. Professor Zhang's exceptional leadership also extends globally. As the chairman of the International Society of Soil Mechanics and Geotechnical Engineering's Technical Committee on Embankment Dams. He also the editor-in-chief for GeoRisk, and also special editor of Geodata and AI, and also associate editor for ASC's Journal of Geotechnical and Geoenvironment Engineering. His outstanding research also recognized by numerous, honors. For example, the ASC's World Pack Award, and also the Chinese National Engineering Award, and also the ISSMG Le Case, Letters Awards, and so on. So without spending more time, I think I also want to just mention one small things. About 5-6 years ago, when I started to look into multi-hazard risk assessment, and then Professor Zhang's work, and then actually stimulate my thinking on that. So today, together with you, I'm really looking forward to hear what Professor Zhang, to talk about their latest research in digital twin in power, urban flood, and landslide emergency management. So Professor Zhang, I give you the floor. Thank you.
Thank you so much. Allow me to upload my file.
Oh, before that, I would like to mention, one more thing. So during the talk, you can put down your question and at the Q&A box, and I'll pick it up, for you after the Professor Zhang's speech. Thank you.
May I confirm you can read my screen?
Yeah,
okay.
All doing well.
Oh, okay. Well, good evening, good afternoon, everybody. It's indeed my great honor to present a Informatics and Multi-Hazard Risk Reduction UNESCO Chair Seminar. I'd like to, first of all, thank Professor Chuhua Liang for offering me this great opportunity. I would also like to thank my teammate, Dr. He Jian, Xiaote, Ji Luyi, Jeffrey, and participants from some of my partnering institutions, for instance, Chinese University of Hong Kong, the University of Hong Kong, the Civil Engineering Development Department of Hong Kong Government, University of California, Berkeley, and Norwegian Geotechnical Institute. So today, I would like to first introduce challenges in city resilience under climate change. then introduce a city digital twin, which is being developed at Hong Kong University of Science and Technology. After that, then I'd like to introduce how the digital twin can be applied to empower emergency management. A lot of larger cities, particularly the 4 Bay areas around the world, and particularly New York, San Francisco, Tokyo, and the Guangdong, Macau, Hong Kong, Greater Bay Area, are subject to some typical hazards. For instance, tsunami, earthquake, rainfall, flood, storm surge. Particularly the Greater Bay Area, including Hong Kong, suffer from water-related hazard. Well, in fact, in terms of number of major floods, cumulative fatalities, and affected area by floods, the Hong Kong Macau area always ranks #1 in the last many years. Hong Kong is relatively prepared for flooding and other type of natural hazards through a lot of efforts in the last decades. For instance, through grain slope protection at the high elevations, through drainage at the middle level of the mountain, through barriers and other protection measures at the foothill to protect any landslide impact, and through concurrent flood storage and drainage facilities in the town, and finally through some coastal protection measures at the outlet. Having said this, Hong Kong still suffered. So right here you can see some typical flood protection measures in Hong Kong. For instance, several drainage tunnels at the middle level, several flood storage, temporary storage tanks in the city. Although we have relatively good facilities, we still face increasing landslide and flood risk under climate change. Just 4 years ago, a central city in China, Zhengzhou city, experienced severe flood damage with roughly 400 deaths. And 2 years ago, well, just 1.5 years ago, Beijing city also experienced a severe flood, leading to 33 deaths. And just a little more than 1 year ago, Hong Kong experienced a huge storm, what we call September 7th century storm. During the storm, our hourly rainfall, 4-hourly rainfall, and 12-hourly rainfall all break record. We got a 12-hour rainfall about 817 millimeter and 1-day rainfall close to 850 millimeter. Indeed, due to climate change, well, the rainfall in Hong Kong and vicinity becomes more frequent and intense. Based on studies of HKUST, CUHK, and Hong Kong U, the project rainfall intensity at the middle of the century will reach roughly 230 millimeter per hour. So we face great challenges. Around us, we'll never forget a huge storm which happened about 40 years ago in Henan, which we call 75 August storm. In that storm, the hourly rainfall intensity reached over 200 millimeter, and daily rainfall, daily maximum rolling rainfall reached about 1,060 millimeter. And about 15 years ago, Taiwan, also near Hong Kong, experienced huge rainstorm with 24-hour rainfall exceeding 1,600 millimeter. Previously, we always describe such a larger storm as something black swan or something unpredictable. But today, as similar events become more and more frequent, perhaps we are not able to say those are unpredictable anymore. In fact, it's our responsibility to make some of the event predictable. Now back to Hong Kong. Hong Kong is a small city, particularly with all the economic center centered on the Hong Kong island. In the last many years, we tried to answer a few questions. For instance, before the last century storm, the biggest ever storm in Hong Kong happened in June 2008, which is about 17 years ago. At that time, the Hong Kong island experienced a storm which is equivalent to about 29% of probable maximum precipitation, and indeed quite severe landslides, debris flow, and flooding occurred on the Hong Kong island. During that storm event, a storm center was actually near the airport, which is relatively remote to Hong Kong people. So there was a question which always faces us: what if the same storm happened at Hong Kong island? So previously we conduct analysis assuming a lot of possible future extreme rainstorms. If we put the same rainstorm on the centered at the Hong Kong island, then that storm will be roughly 44% of PMP, or probable maximum precipitation. So if that happened on Hong Kong island, then more severe landslide, debris flow, and flooding will happen. Also, I'd like to answer the question: whoa, what if the 1975 August Henan storm happened in Hong Kong? Then we conduct again a stress test analysis, impose the Henan storm on Hong Kong, and find out more severe hazards, obviously multi-hazard. And if you like to answer, well, what if the Morocco storm, which happened in Taiwan, happened at the center of Hong Kong, then we would expect more severe consequences. At this stage, one of the largest or most important economic center which is being considered or being constructed is what we call Northern Metropolis, which is the northern part of Hong Kong in border of Shenzhen City. Now, if we impose largest possible storm in Hong Kong, or the storm with a magnitude similar to the Morocco, then you can find out majority of so-called Northern Metropolis could be severely flooded. Therefore, we have a lot to do to mitigate flood risk and prepare for changing climate. Now, in the changing climate, what do we do? Well, in fact, now we are in the so-called digital age, right? Then, to enhance natural hazard emergency management, what do we do? Well, certainly we should go digital. Well, in fact, in Hong Kong, we have a slope safety technical review board who constantly recommend a digital twin for slope stability, and also in the most recent government chief executive policy address, the chief executive promised to introduce a mechanism to mobilize the government at all levels to enhance emergency management. Given those background, at the HQSD, we're working on developing a unique city-scale digital twin for Hong Kong. The purpose of the digital twin is to sense, simulate, visualize, and synchronize the dual dynamics of natural hazards and societal responses in order to enhance risk management capabilities in this region. At this time, we aim to establish a new paradigm for disaster emergency management science in the digital era. Now, this digital twin consists of four major components. The first component is so-called digitized reality. Yeah, we like to digitize for the reality, digitize all the facilities for flood control and landslide safety management. The second task for constructing this digital twin is to build a space, terrestrial, and the air, also called space area and terrestrial sensing network. And the third task is to develop simulation engines, and the fourth task is to develop tools for emergency risk management. So in the last 20 minutes or so, I'd like to introduce each of the 4 components. Start with digitization. Well, indeed, in Hong Kong, we are pretty much privileged because the government support our study strongly and provided us a lot of city data. For instance, we got all the 60,000 man-made slope features. We got record of roughly 120,000 past landslides. We got access to all the rain gauge data and high resolution LiDAR DEM data for the ground, together with a lot of other data necessary for constructing the digital twin. The first thing we need to consider is to digitize the buildings and the infrastructure in Hong Kong. Altogether, we have roughly 340,000 buildings around Hong Kong. And well, in fact, in the last many years, the government has made an effort to digitize all those. Okay. So today we have roughly 215,000 buildings digitized to lightweight BIM, and about 11,000 buildings digitized to relatively more detailed BIM model. For instance, the entire campus of Université or my university has been digitized by a team in our civil engineering department led by Professor Zhang. We have also digitized the drainage network for Hong Kong. The underground drainage network consists of roughly 220,000 sections of drainage pipes, some trunk, some tributary pipes. So after digitization, so when we click whatever piece of pipeline, then the information of the pipeline will be shown. The pipeline system has also been integrated into hydrodynamic model for flooding analysis. Next thing we need to take care of or to digitize landslide mitigation structures, including over 140 what we call rigid barriers for landslide study. So what we did, we will use drone to get multi-view pictures, and then you scan to BIM to create BIM models, and then get back to 3D photorealistic models. We have also digitized other landslide mitigation measures like soil nails, drainage channels around all the slope features. The second task is what we call sensing, space terrestrial sensing system. The sensing system for the digital twin consists of static and dynamic. Because dynamic portion include, first of all, the radar image provided from Hong Kong Observatory and the rain gauge network, which cover entire Hong Kong, with each gauge roughly taking care of about 10 square kilometers of land. So this is the image for the rainfall process for the September 7th century storm. The government CEDD Geotechnical Engineering Office has also installed sensors on several rigid barriers, so that anytime if a particular rigid barrier is impacted by rock, by rock fall or by debris flow, then signal will be sent to the control office. Also, the depths of debris would be measured using sensors in the system. When we talk about a city scale digital twin, we really need numerous sensors. But one measure which we trust most is space sensing or remote sensing. In the last many years, HKUST has attempted to build a so-called Radarbird constellation, which consists of an optical satellite, a CO2 satellite, and a soil satellite. Well, in fact, our team, with great help from the university and from the industry, has launched a high-resolution optical satellite in last August. So here's the moment of satellite launching. So being the team member, we are lucky enough to be on site watching the launching of our optical satellite. By the way, the optical satellite has a resolution of 0.5 meter, which is more than sufficient to identify landslides and other natural hazards. Indeed, this kind of high resolution optical satellite is very useful. So here's a short video introducing the operation of satellite and how it is used for identifying landslides. During the September 7 storm a year ago, a lot of landslides have been triggered. So with the help of satellite image, we are able to identify was a landslide timely. For this purpose, a relatively efficient code has been written so that we can simply just input image before the rainfall event and after the rainfall event. So with the two images input, then this machine learning algorithm is able to identify the landslide very quickly and efficiently. So certainly we can identify the landslide and compare with observation. So on the right, you can find out some relatively larger size landslide, the image before and after the rainstorm. Next, I would like to introduce roughly how the digital twin can be applied to empower emergency management. Indeed, one of the big purpose of digital twin is for emergency management. But of course, emergency management is not the only service which a digital twin can provide. Usually, a digital twin, particularly nowadays, a lot of digital twins are built for the purpose of asset management. So, of course, we can also extend the digital twin for other purposes like real-time monitoring and emergency management. Now take an example. So how we use the digital twin for asset management. So on the screen is a slope, the man-made slope feature. So once we digitize digital twin and then connect some real-time instrument which observe this feature, then we are able to, from digital twin, observe the risk level of this feature and also find out, well, if something wrong with the landslide, with the slope, then how many people, how many buildings could be affected? Well, in fact, this feature is simply just one of a lot of slope features, right? On the digital twin, we can rotate it around and then find out if this particular feature got a problem and material rundown and heat the neighborhood, then well, how many buildings, how many people could be affected by the failure of such a slope feature. Yeah, certainly we can use the digital twin as a platform for real-time monitoring of infrastructure, flood control facilities, and landslide control facilities. So here's a kind of real-time monitoring showing. First of all, rain, rainfield, real-time rainfield, and landslide reported to the government through the public, and any particular issues which would be reported. And this screen shows, again, potential incidents, including traffic incident, by the way, okay, and any possible landslides and some other events. So indeed, the digital twin constitute a pretty nice platform for real-time assessment. Well, when we talk about emergency management, nowadays we like to go quantitative. Yeah, we need to go from qualitative risk management to quantitative risk management. To do so, we need to estimate the consequences of any adverse effect caused by either flooding or landslide. But indeed, in the last few years, we have developed both statistical-based or both statistical-based and machine learning-based rapid risk assessment systems. So here is a product which we call Polar, developed by Dr. He Zhang and others, other students. Polar is a almost near real-time landslide risk assessment system, which consider, first of all, rainfield. So based on rainfield, then look at potential landslides, number and size of landslide, then area which could be impacted by landslide through mobility studies. So after that, then through vulnerability studies, we were able to assess, right, how badly the buildings could be affected and how badly human beings could be affected. Finally, we are able to evaluate so-called societal risk, which basically total number of buildings affected or potential number of people which could be killed in unfavorable events. And here is another version based on AI or based on machine learning. So here is real-time risk assessment outcome based on Polar. On the left, upper left is the rainfield, real-time rainfield. By the way, in Hong Kong, rainfield could be updated every 3 minutes. And this analysis takes just like 2 or 3 minutes. Therefore, the risk assessment outcome is will be only just with a 2 or 3 minutes delay. So on the right, upper right is occurrence and distribution of landslides, and the lower left, distribution of possibly affected buildings, and lower right, number of fatalities, potential number of fatalities. So we are able to provide such near instant assessment of landslide risk. And compare, certainly we need to calibrate the models and compare the assessment, the model assessment, and with reality. One of the major advancements made in the last 1 or 2 years is what we call rainfall nowcasting, and therefore flood and landslide nowcasting. Well, in Hong Kong, we followed HKO, work with HKO or Hong Kong Observatory. Now Hong Kong Observatory offer 2-hour rainfall nowcasting, which is now roughly 9:30. So then HKO is able to forecast rainfall in the future 2 hours. So future half hour, 1 hour, 1.5 hour, and 2 hours, and update such forecasting every 12 minutes. The principle of nowcasting is relatively simple. First of all, we got so real-time radar reflectivity observation and real-time rain gauge data. So by combining the two, then we can get the rainfield. instant real-time rainfall. At the same time, so based on radar reflectivity at different times, the HKL is able to obtain what we call motion field of the reflectivity observation. So based on such rainfall motion field, then it's able to forecast the rain field in the next 2 hours. Right. Then with a nowcasted rain field as the input, then we are able to estimate or to forecast a landslide or flooding situation in the coming 2 hours. For instance, that's examples of nowcasting for the century, the September 7th century storm. Black line means real-time measurement, and the dashed line basically 2-hour forecasting. So in this graph, based on the rainfield nowcasting, we are able to predict the number of landslides, number of buildings which could be affected by landslide, and number of potential fatalities which could be resulted from the landslide. So such 2-hour forecasting could be quite important, so that with the 2-hour forecasting, right, the government and the individuals, the public, will be able to take actions with 2-hour advance notice. 3 examples of, again, September rainfall. So for instance, at 10 p.m., so we are able to forecast 1-hour rainfall and forecast 2-hour rainfall, and then compare with measured rainfall 1 hour after and 2 hours after. At the same time, we are able to based on rainfall to forecast potential landslide at any future time, potential number of buildings affected, and the potential fatality anytime. So ahead of time. So half hour, 1 hour, 1.5 hour, 2 hours ahead of time. So this is basically forecasting based on the real information obtained at 10 p.m. and then 11 p.m., 12 p.m., and 1 p.m. At this time, 2-hour nowcasting, rainfall nowcasting, has been shown to be relatively reliable, but a lot of effort must be made for longer term forecasting. For instance, 6-hour nowcasting. Next, so in addition to landslide analysis, we're able to develop hydrodynamic-based and AI-assisted flooding early warning. So to do early warning, so what we need to do is to come up with some fast calculation model. So this is what we call AI-driven super resolution rapid flood analysis model, which is basically hydraulic-based model. So how we make it really quick, essentially we first use coarse grade to conduct flooding analysis, and then use fine grade analysis outcome and the fine grade topography information to train the coarse grade analysis outcome, so that we obtain the fine resolution outcome, flood outcome. Well, this method actually accelerated analysis by around 6,000 times, so that we are able to cover entire Hong Kong of about 1,000 square kilometers within just a few minutes. So hydrodynamic analysis within just 3 minutes, around 3 minutes. So with such analysis, we are able to identify or to observe the flooding process in the neighborhood. And so when we come up with a particular highway or MTR underground rail, we would able to observe exactly when this highway would be affected, how long this piece of highway would be affected, because eventually the flood would recede and the factor time would be just limited. So with such analysis, particularly with ability of nowcasting, so it's possible to help either government or insurance companies or the public take some advanced action. Or in fact, last May, Hong Kong experiences the second largest short period of storm, and the storm center happened to be near our university. In a very just short period of time, a lot of car parking spaces was inundated. So to some particular industry like insurance industry, so it would be nice such a scenario be forecasted even 30 minutes. Then hopefully signal will be sent to the owners of those cars and action could be taken in advance. Otherwise, the cost like this, a lot of flooded car was really, really costly. So with such forecasting and advance notice, so it's possible for the authority to take some advance action for traffic management and sometimes, if possible, to allocate some resource to prevent the propagation of a hazard to some critical areas. We have also developed augmented virtual reality visualization tools so that we can showcase to the public for public education and for exercises, for fire drill or similar to fire drill for flood drills and landslide drills, and to help optimize evacuation routes. And lastly, most recently, we are allowed to connect our digital twin to numerous cameras for traffic control. So with this, then it's possible to observe at any particular time traffic condition, flood condition, and whether a particular area has been affected by landslides. So this really enhances our observational capability of the digital twin. Lastly, I'd like to just draw a few conclusions. So we're working on a unique simulation-enabled city-scale digital twin for Hong Kong slope safety and flood control system and the built environment. This digital twin serves as an all-in-one platform for interactive decision-making, emergency management, and public education. And this digital twin is powered by AI-driven physics-based simulation engines and risk assessment engines. And we believe the implementation of digital twin into a government risk management system would significantly enhance the city resilience. So with this, I'd like to thank all of you for your patience.